Alright, so quickly, I apologize. Umang, here's the definition of simply connected. Craig had a beautiful wax equivocal with mathematics, and then who said no holes?
That was also me.
And there was also Craig who then said no holes. We now have holomorphic functions on a simply connected region have primitives. And we have a set, we have an example here where it is not simply connected. So we don't expect to be able to have a primitive here. How did we prove a primitive existed? What did we do?
Would that involve, like, we took a point and then we tried to take another point, like F, like V plus H?
Yes. So, what did we do? We started off with a disk here and some points in here, and we took a special path like this. And we used a rectilinear path to create a primitive. And I talked to you, I think, during one of the proofs from the book where they said that in these toy contours we can still create primitives. And the book kind of waved their hands and said that this could be done. And we talked a little bit about the difficulties. What if I gave you, a region like this to make it primitive? Are you allowed to do something like this? Do you have to only be moving maybe like this? And we talked about, the difficulty of trying to prove. So one of the things that's nice is you can use this idea to create a local primitive. And then from this you want to build up a function from that. And so the key idea is, at the end of the day, we want something that's path independent. If I have a primitive, does my integration depend on the path? No. So primitive, it exists, primitive implies integrals are path independent, i.e. only depend on endpoints. And so we had all those beautiful theorems, and what we could do is we could say, well, look, if I have a primitive here, once I have a primitive, we have an easy result that the integral over any closed curve is 0. So now take one half of it to go up, and take the other half to come down. Those two integrals have to cancel out, so if I then just flip the other one, it has to give me the same value. And for those of you in physics, think of conservative force. Okay? So once you have a primitive, the integrals are path independent. All that matters is how I get there. So what we want to do is we want to show that if I have a simply connected region, I can create a primitive. And so the idea is to create a primitive on a simply connected region, go from local to global. Okay. What we want to do is we want to start building up our primitive just with local information. And so what I'm going to do is I'm going to just state the main result. I'm not going to go into the proof. The proof uses just some basic topology, but this is not really a prereq for the class. And so the theorem, F is holomorphic on a simply connected open omega, then F has a primitive. Umang will have a surprise today. There were a lot of people drinking at the conference, but I was not one of them. Okay. So, do you think we need any other assumptions? Is it enough to just assume that it's simply connected to get a primitive? Do I want to assume my function is non-constant? Why not?
Because every constant has a primitive.
Every constant has a primitive, right? So for some of the theorems, give me a theorem where if my function was constant, the conclusion no longer held.
Max modulus, it still holds.
Max modulus still holds. But there was one very similar, very close to max modulus.
Open mapping.
Open mapping, right? If my function is constant, then I'm not going to get an open map. Right? Here, if my function is constant, the analysis is significantly easier. Okay? So let's imagine I have 2 points, and so this will be a sketch of the proof. Literally, a sketch. Okay? I have 2 points, and I have some curve that connects them. I need to show that I get the same answer no matter what curve I use. So the main idea you do is if you have 2 different curves, you look at a continuous deformation. Frequently, you might be able to do something nice. Maybe you have the curve gamma 0 and the curve gamma 1. Maybe you can let gamma t be gamma 0, I'm sorry, be 1 minus t gamma 0 plus t gamma 1. This won't always be in the space, but if this is in the space, this is really nice. At time 0, what curve does this look like? Gamma 0. Time 1, what curve is this?
Gamma 1.
And so this lets you walk from gamma 0 to gamma 1. Sometimes you might not be able to do that. You might have, maybe your space has this big indentation in here. And so you might have some trouble, but let's look locally. So here's some curve. Here's another curve which is close to my curve. And all I need to do is show that these 2 curves have the same integral. And then what I'll do is I can slowly walk from my initial curve to my other curve. So I may not always be able to do this, but if the curves are homotopic, that means I can deform from one curve to another. And if I can deform from one curve to another, if I can just show each small change doesn't change the value of the integral, I'm okay. So the idea, I'm just going to sketch it, is to draw lots of circles. Circles are good. What kind of circles are these, other than poorly drawn?
Cover.
So they cover, the circles cover the curves. What else do you notice about the circles? Circles cover the curve.
Do they have to be the same size?
They don't have to be the same size.
Finite number.
Finite number. Finite number. Variable size. There's one additional property of these circles that I care about. I'm sorry? They intersect. Always intersect. So that's extremely important. So what I can do is I can take 2 points here that are in the first circle and the second circle. Then I'll take 2 points here that are in the second circle and the third circle. Then I'll take 2 points here. And I'll march down like this. So the book does a nice job of going through the proof, so I just want to sketch the idea. Do I have a primitive on each of these circles?
Yeah.
Yeah, why?
It's open circle.
Open circle, yes. Right? Each circle has a primitive. Yay. If the world was really, really nice, what would you say about the primitive on this circle and the primitive on that circle?
The same.
They're the same. Is the world really nice? No. You'll find out when you get there. Okay, so the world is not always nice. How bad can the world be? How much could the primitives differ?
Constant.
Constant, right? I have 2 different primitives. They have the same derivative. So what's the only way that they could differ? They differ by a constant. Well, when I'm integrating, all that matters is the endpoints. I'm going to subtract. The constants will cancel. For the physicists again, and yes, there's an advantage to being a physicist today, look at changes in potential energy. Does it matter where you define ground 0 to be? No. All that matters is the change in potential. I can have ground 0 at the center of the earth, at the table, at the floor, at the ceiling. Any of these are all fine. All that matters is the difference in potential energy. When I'm integrating for the fundamental thing of calculus, we always say, let f be a function, let f be a function, let big F be a. I was a postdoc at the Ohio State University. Okay, it is the Ohio State University. It is the central university in Ohio. Okay? In calculus, you don't say the antiderivative. you say a antiderivative. Why in the fundamental theorem of calculus do I say a antiderivative rather than the antiderivative?
Because there's multiple.
There's multiple. So, am I in trouble? Do I have to worry about which one I take? No, why don't I have to worry?
They give the same thing.
They give the same thing. All that matters is the difference. Is I need f of b, big F of b, minus big F of a. And so since I only need the difference, it's perfectly fine that they differ by a constant.
So where did we use the fact that they have to all be intersecting?
Well, we're now going to use that to basically walk down
Oh.
and show that these integrals are the same.
Okay.
And so when I want to calculate the integral along this path, it's going to end up to becoming just this minus this. And the changes in things over here won't really matter. So again, the primitive here, if I'm using this circle, could be different than the primitive from this circle,
Oh, I see.
but only by a constant.
Some sort of transitivity will work?
Yep. And so if I add an extra constant here and I add the extra constant here, it's not going to be a big deal. The other thing which you can try to do is you can try to complete paths. So if I'm walking down like this, I mean, here's another thing for you to try if you're interested. When you see something like this in these points, what kind of lines would you like to add? Yeah, add a line coming here like this, and add a line going in the other direction, coming here like this. And all those interior lines will cancel. What's going to be the integral over this? 0. And so basically have these things march down. Okay, so that's another way to try to prove the theorem. Okay, so there's lots of different approaches. The main result is that if you're holomorphic on a simply connected omega, then f has a primitive. If on an exam I ever want you to prove something from first principles, I will say, using only such and such a fact, prove blah. Okay? As a working mathematician, there's no desire to try to handicap yourself and say, I can prove this theorem without using, if you have a theorem, use it. There is a time in mathematics where you sometimes want to see how deep is a result. Do I need the full power of this statement to prove it, or does it follow more elementarily? It is extremely confusing to keep track of what was proved at what time, in the order of which we do things. And so for the most part, integrate over contours. If you have two curves that are homotopic, if you can deform one to the other without leaving the region, then the integral over one is the same as the integral over the other. And that's a really nice fact. Okay, so this is enough on the topology. This is the second time this semester where we've come across a situation where we needed some topology. Does anybody remember the first one? There was one theorem where we proved locally something happened, and then to pass from the local to the global, we needed to use a little bit of topology. Does anybody remember? It was the set U union V, where U and V were both open sets. Does that bring back any memories? It was points of accumulation. If there was a point of accumulation, we showed that locally there was some small disk. Inside that disk, the function was identically 0. And then we looked at the set of all points where the function was 0, and we showed that that was an open set. We also showed it was a closed set. We then showed that this would allow us to decompose our space as to U union V. We could decompose our open set in terms of the union of two open sets. And that violated the connectedness assumption we made about our region. So this is the second time in the semester where we're really using topology. If you are going to graduate school in mathematics, how many of you are considering doing this to yourself? Okay, a lot of programs will want to make sure you have a year of algebra, a year of analysis, including measure theory, a year of complex analysis, and a topology, at least one topology course, so that you have an understanding of these basics. Okay, now, I'll put natural there, but it's not time to talk about the logarithm. Alright, so this is now section 6, right? And then after this, we're going to get into chapter 5. We will bypass Fourier analysis for now, and we will swing back to Fourier analysis later in the semester. I'm going to assume, just because I have a couple of physicists in the class, that you will want to see that the Heisenberg uncertainty principle is actually a consequence of Fourier analysis. And so, if you don't want to see that, just please nod your head so that I feel better, putting this into the curriculum. Okay? What's the physics content? The physics content is that these mathematical formalisms actually correspond to things in reality. But you can view the Heisenberg uncertainty principle as a consequence of Fourier analysis. How many of you have done any Fourier analysis? How many of you have done a lot of Fourier analysis? Okay. Another great subject to get into in depth. What is wrong in trying to define the logarithm of a complex number?
The angle.
The angle, right? The log of r e to the I theta, the log of r is no problem, and then calling it I theta is the problem. Because I could look at the log of r e to the I theta plus 2 pi n, and that would be the log of r plus I theta plus 2 pi n. Well, one solution is to just declare that angles must be between
0 to pi.
0 and 2 pi, or maybe minus pi and pi, or maybe pi halves and 5 pi over 2, you know. So you have to pick some region of length 2 pi and declare all angles to be in that. The problem is sometimes you have curves that wind around, and as you do that, the angle keeps increasing continuously. You don't want the angle to somehow suddenly decrease. So imagine, you have your path gamma going like this. Okay? And so everyone is walking like this. And so I can look at each moment in time, what is my angle? My angle starts off at 0, gets up to 2 pi over here. If I reset my angle to 0, all of a sudden I have a discontinuity. And I don't want to have discontinuities. So there's a couple of solutions. The solution I prefer the most is to just basically karate chop the plane like this. And you basically now say, there's this cut in the plane, and thou shalt not cross thy cut. And so now I can actually do a path like this. So now, I start off like this, and when I come to this line, I can't go over. And so I have to back up somehow. Maybe I try again later, nope. Try again later, nope. Keeps going off to infinity, I get bored, and I just come home and give up. Or, instead of coming home, well, let me try to get a nope. No. Alright, I give up. Okay? That's an acceptable solution. Is to basically just prohibit yourself from cutting across some line.
Doesn't that change the curve?
Well, no, what it basically says is you can't use that curve anymore. I will not study that curve. Okay, if you have any problems with this, just think of all the functions we've already excluded this semester. Okay? We've already excluded so many functions of the variables x and y. What's a little bit more restrictiveness among friends, right? So we've already killed so many functions. We've already said we're not going to look at that. We're only going to look at functions of the form x plus iy. They've got to be a function of that because that's nice. We're going to do now something to our curves. Yes?
Isn't this equivalent to the restricting yourself to 2 pi angle from that initial angle to that plus 2 pi? Because if you can trace out any curve on a slip plane, can't the angle never be greater than 2 pi difference?
Essentially, yes. It's basically the same thing as restricting yourself to, I don't allow myself to go all the way around. But and again, it doesn't have to necessarily be at 2 pi. I can go backwards as well, and depending on how I have things defined. But yes, I'm basically saying a certain angle is not, I'm not going to allow myself to get there. Now, instead of using a line like this, could I do something like that going off to infinity? Yes, it's a lot more complicated to draw and deal with. So for the most part, people use straight lines. So what we're doing is we're giving up. Question?
It looks like a photon.
Looks like what?
It looks like a photon.
Oh. Yeah, it actually does look like a photon. But it's not going to split off into anything like that. We are giving up on defining the logarithm of all numbers. How do you feel? So some of you seem to be quite upset over this fact that we're not going to define the logarithm for all numbers. Who has some trepidation about this? Okay. What's the log of 0?
1.
not gonna put any.
You don't talk about that.
We don't talk about that. Right. So you have a history of excluding numbers in logarithms, right? All I'm doing is infinitely excluding, I'm just taking what you're doing and taking it to the next level. What's the logarithm of -5? Right. We don't talk about the logarithm of -5. Right? So really, that's what we're doing. What we're saying is, we have the logarithm function, which is initially defined on the reals. So log, actually it's initially defined on r plus the positive reals to r. And now we want to extend it. And the thing is, we can't extend it to all of C. Okay? So we extend to omega a simply connected open subset of C. And again, there will be lots of different simply connected open subsets we can take. The simplest one, the most canonical, is the one that does include 0 and 1. I'm sorry, that does include 0, does include the negative numbers, but does include the number 1. Okay, so let me just... Alright, so... let omega be simply connected. 0 is not in omega, 1 is in omega. Okay? We move so let's try to think what omega has to look like. So here's 0, here's 1, I have 1. I have a simply connected region. Could my region look like this? Is this a possible omega? And I won't put a dot there, so could this be my region? Why not?
There's a hole connected.
There's a hole in it. So what do I have to do with my hole?
It's gotta be outside.
It's got to be outside. So possibilities are the following. I could do something like this and just say, I don't care about you. Right? That's one possibility. Another possibility is to do some kind of cut like this. And these are all the points not in omega. Is that simply connected? Yeah, if this goes off to infinity, I don't have to worry about, can I somehow sneak around and come out? No. So I have basically two possibilities. If things around 0 are inside my region, I've got to have a cut like this going off to infinity. If 0 is not inside my region, then it's much nicer. If the region looks like this, it's really not that hard to define a logarithm. So the question is, how do we define a logarithm? How do we define, and let's give it a name. So it should be obvious, but why am I calling it log sub omega?
Because it depends on...
Because it depends on omega.
Omega, yeah.
Right? Notation should be good, right? This notation tells me I'm going to define a logarithm, and the definition of the logarithm will depend on the region. And so it's the same thing with the different choices I have for the cuts. If I cut things differently, if I made the strange decision to throw away the positive reals rather than the negative reals,
Can't you not do that? 'Cause you need one.
well then, I would have a different set. I can make a definition of the logarithm work. As long as it's simply connected, I can do that. But I would no longer be in this situation. Why do I want to include 1? Why do I want to include the positive reals in my region?
To make it stronger, like, apply back to both.
Apply back to what? You're close.
Like, we can use complex stuff and then apply it back to the same function will also apply to the reals.
Oh, we want to extend the real valued function. If I want to extend the real valued function, it should be defined where the real valued function is. Right? And so if I throw away the positive reals, I lose the fact that it's directly extending this. But there could be some problems where, depending on the situation, where you might want to actually throw away the positives. Strange, but for them it's possible. So how would we define the logarithm? So whenever you're stuck, go back to calculus, go back to things you've seen earlier. How is the logarithm defined? The antiderivative of what?
1 over
Okay, so log of x is the antiderivative of 1 over x. This suggests how we should define the logarithm. Let f of z be 1 over z. Define the log of omega of f of z to be the antiderivative. Alright, so I want to integrate then f of z, well, so let's say f of w dw. Where do you think I should integrate? If I integrate along a closed curve, what might I get? I might get 0. So I probably don't want to integrate over a closed curve. Another way of looking at this is I'm finding what of 1 over z? I'm finding its
Taylor series.
No, it's Taylor series. Taylor series involves differentiation. If I'm integrating, I'm finding its antiderivative. Right, I was about to say, you're speaking in real analysis now. We want to speak in complex analysis, right? Rather than saying we're finding its antiderivative or integral, let's introduce a new word, primitive. Okay? We're defining its primitive. How did we define primitives before? What did we do? There was a reason today's lecture started off with homotopic and how do we define a primitive on an open circle. How did we do that? So how do we define primitives on an open circle of a holomorphic function? What did I do to get a primitive? I started with an open circle, I took a special point, and if I want to find the primitive at some point z, I looked at a very special curve. And so maybe I will have this defined as gamma z, where gamma z is a path from blah to blah. So where do you think the path should end? Z, right? Z should be playing some role in this game, right? I'm trying to define the logarithm at the point z. Z should somehow play a role. Where should the path start? And please don't say z. 1. Why 1?
Because 0 is not only special.
1 is the only special point we have, right? I tell you, 1 is in it. What if I were to make the strange decision and try to start at the point 5? 5 might not be in it. What do you think the change would be if I started at 5 rather than 1? Let's say 5 is actually in my set.
Well, wouldn't 5 be in your set for the whole reals?
Well, if I want the whole reals, yes. Right now I've just told you I know 1 is in the set and 0 is not in the set. I've just given you minimal information. What if 5 happens to be in the set? What would be the difference if I start at 5 rather than at 1? Constant. So the whole point is I would only change the value by a constant. Oh, that's not a problem. And in fact, I don't expect the primitive to be unique. So for example, let's let gamma AB be the path from A to B. Then the integral over gamma AB of f of z dz is the integral over gamma c to a let me write down the points. So here's the point A, here's the point B, here's another point C. Here's one path I could take from A to B, here's a path I could take from B. And so what do they differ by? A to C. So one possibility is they differ by an integral from A to C. And now the the hope would be that these two would now be the same. So this should be gamma AC of f plus the integral of gamma CB of f. And then they would be equal. Now, that's assuming that I have enough information at my disposal to say the integral over this curve is the same as the integral over that curve. Do I have that? Yes. It's simply connected in holomorphic functions. So, simply connected plus holomorphic, therefore the integral over gamma AB is the integral over gamma AC plus the integral over gamma CB. Right? That's why I'm using the results from earlier today. So the integral over this is the same as the integral over this. So the only difference between the integral from A to B and the integral from C to B is this little bit of the integral from A to C. But we're adding that to every single choice. And if we're adding it to every single choice, it's just a constant. So all we've done is we've changed the antiderivative, or we've changed the primitive by a constant. So it's not a big deal where you choose your starting point. So different starting points give differences of a constant. Okay, that's not so bad. Can you say something very nice about what the log of 1 would be? So I'm integrating along a path from 1 to 1. Right? This is like the dream integral. Right? What is the integral from 1 to 1 of 1 over z? Yeah. Can you refine that to be a little bit more certain?
Almost definitely zero.
All right, that's not a measure theory. We're not doing almost surely zero. You go a little bit stronger than that. It's 0, right? That's the whole point. So note the log of 1 is 0 if stopped at 1. Okay. And that's one of the reasons why we want to start our integration at 1. It's going to allow us to reproduce everything we've seen before. Okay? So again, I'm trying to motivate the definition of the logarithm. This is one of the most important concepts in complex analysis. Okay? Question?
Should it be log of C equals?
Log of z. Yes. Thank you. Yes, thank you. Right. So the log of z would be this. So we have something that's looking very promising. The log of 1 is 0. This will make sense if I take a region like this. The function is defined. We've just shown that it's independent of path. And that's because it's simply connected. So when I say, where is a path? The fact that I'm using a and not the is quite important. If I had to choose a specific path, I could potentially do that, but then I would need to know maybe a little bit more shape of what the region looks like. And so if I give you a circle, it's no problem to talk about, polygonal, go east-west, then go north-south to get to your point. If I give you a general toy contour, it could be a little bit harder to describe what the path is. But what we've just seen earlier today, and again, I haven't finished the proof, it's in the book, it uses a small amount of topology, is that if you have a simply connected region, then the integral over two homotopic curves are the same. And thus, if you're defining a primitive, you might as well use any curve you want. So now we're really close to having a definition of the logarithm. The only thing is we might want to check that it agrees with a few other things. So what else would you like the logarithm to satisfy?
The properties.
Okay.
Multiply and side add.
Okay, so something a little bit more basic than that. So we have the log of 1 is 0.
Oh.
Anything else you want to make sure of?
What do you just erase?
Yes, that's deliberately erased. What else do you want to make sure the log satisfies?
It doesn't exist for 0 and negative years.
Okay, so it won't exist for 0 because 0 is not in my set, so I can't have a curve. So good, so we're not going to be able to assign values to the log of 0. Excellent. We're not going to be able to assign the logarithms to negative integers or negative real numbers. Good. But what other... We know something else about the logarithm.
Log of the exponent.
So those are the log properties. But we're trying to extend the logarithm function. I've checked that the logarithm of 1 is 0. What else should I check?
The log of
Oh,
exponential
derivative
derivative of the log.
I'm sorry?
Derivative of the log.
So 1 is the derivative, but there's something even more basic than
What
just the...
about if x equals log of z, then either get x equals z?
I'll say close enough.
Okay.
We want to make sure that the logarithm agrees with the original definition of the logarithm for real numbers. If I'm extending the definition of the logarithm, my definition should at least agree on the same set.
That's exactly right.
Well, you were close to that when you were saying that the exponential of the logarithm,
Yeah.
because that's then coming back to the definition of the logarithm for a real number. So that's what I'm saying, it's a little bit hard to pass. But, you know, does this agree with the old logarithm? So here's 0, here's 1, here's a real number r. I'll just assume r is greater than 1 because I want to put it there. It doesn't really matter. Can somebody give me a path?
From what to what?
From 1 to r.
Straight line.
Straight line. So here, we need to say a little bit about omega. I just said omega was an open set. Let's say omega equals the complex numbers minus the interval minus infinity to 0. So this is the typical, I think they call it the principal branch. Principal branch of the log. So I have the path from 1 to r is in my region. Is it possible to have a simply connected region that has 1 in r but does not have stuff from 1 to r in it? Yeah, I mean, I could give you like the half donut. Here's 1, here's r, here's 0. I could give you something like that, and I might not be able to integrate along that path. So let's assume we have the whole real line. Why? Well, I want to make sure that this generalizes the definition of the logarithm on the positive reals. If it's going to generalize the definition of the logarithm on the positive reals, what can you say about the positive reals in my set?
You want them there?
I want them there, right? If I'm trying to show that it generalizes, they better be there. So is it really a serious assumption to assume omega contains the positive reals if I'm trying to show that this definition generalizes the notion of the logarithm on the positive reals? No. So now we chose the simplest possible path from 1 to r. And so our definition now is the log of r is the integral over gamma of r of 1 over w dw. But this is not a very hard path to parameterize. Right? This is just the integral from 1 to r of 1 over x dx. What is the integral of 1 over x? Right, not like natural log, just to natural log of r minus natural log of 1, which is the natural log of r. Okay, so the definition at least agrees with the definition of the logarithm before. What else would you like to show?
Properties.
Properties. So there was a period of time when I was, taking English classes in school, and they would never call on me, and I would sometimes just prove the log laws for fun, and just see if the teacher would notice how much math I'm doing. And sadly, nope, never. How would you prove the log laws? Do you remember the standard proofs of the log laws?
Yeah, you would convert to e to the power and then split it in here.
So the log base b of x, let's say that equals x1 equals y1. The log base b of x2 is y2. The log base b of x1, x2, well, x1 is just b to the y1. So this is the log base b of b to the y1 b to the y2. This is the log base b of b to the y1 plus y2. So, how many powers of b do I need to get b to the y1 plus y2? y1 plus y2. Okay? So the question is, does this hold for our region? So now, here's 0, and the branch cut going to infinity. Here's 1. We'll call it Z1, Z2. And so I've got some path here, some path here. Here's a path from Z1 to Z2. Is that the path I want? Where do I want to go? So I want to go to their product. Where's Z1 times Z2?
Somewhere.
Somewhere. Thank you.
You're welcome.
Can you be more specific?
Well, it may not be in our region.
It may not be in our region. So Z1, Z2 may be outside the region. Can anybody give me an example of Z1 and Z2 where the product is outside the region? I times I is -1. So I will leave it to you to ponder how much of our log laws collapse. What assumption would you like to make about Z1 times Z2?
They're not equal.
Not negative.
So maybe assume Z1, Z2 is in the region. So there's a nice extra, right? You know, step one, if you want to talk about something, make sure it exists, make sure it's in the realm. So I am not allowed to talk to you about my political views. Your other professors, especially those in political science, should not be talking to you about their political views. Right? That is not in the realm of what I am authorized to talk to you about. I am authorized to talk to you about the logarithm. I can talk to you about mathematics, consequences of mathematics, some career advice. That stuff is okay. That's the legal domain for me. For a problem like this, if Z1, Z2 is not even in your region, it makes no sense talking about what is the log of Z1, Z2. But what if you assume that Z1 times Z2 is in your region? What if you take the principal branch cut, throw away the negative reals and 0, then is the log of the product the sum of the logs? So I will leave that as an exercise for you guys to figure out and try to figure out, is the log of the product the sum of the logs? Okay. Alright, so we have just a little bit more on the logarithm to do. I need to show that the derivative of the logarithm is 1 over z. That's not so bad. It's the exponential log. So we'll finish up the logarithms on Wednesday, and then we will start chapter 5. So I will email everybody exactly what the homework is going to be. We will operate under the assumption that this Friday will be Mountain Day. If you haven't signed up for the Putnam and you want to do so, we are so close to having 2% of the campus take it. We're at, I think, 50 students right now. 50 students. So we need just a few more people. You get 3 homework exemptions if you haven't signed up already. Okay?
Do you have my name already?
I believe.